Hello again, and welcome to the third installment of the fixed wing modeling control lectures for robot dynamics. So this is the last one, and as the title slide says, we're going to go into fixed wing control. So first off, control of airplanes isn't so easy. We're inherently nonlinear in our model, especially in the longitudinal axis, for example, with respect to airspeed. There's low control authority, often actuator saturation, double integrator characteristics, and we are an under-actuated system. So what kind of controller would we potentially want to use? There's been many applied to fixed wing vehicles in the past, anywhere from typical cascaded PID loops to full-on nonlinear model predictive control approaches. So what might influence one's decision on the given controller? First thing here we should consider is, especially for small fixed wing planes, is computational power. So if all that's on board is a microcontroller, then we of course are limiting ourselves to things maybe in analytic form or that don't need to run through QP solvers. So something like an LQR that's kind of fixed output, also PID would work for this. Anything with iterative solving is probably out of the question. If we do have an onboard computer, the other thing, or that could run these other more advanced algorithms, the other consideration should further be that the size, so literally dimensions of the computer, does it fit into the plane if it's a small plane, and the weight. So every gram we add to a small fixed wing UAV is a count against its either range or endurance performance, and also could be a count against how much payload for a given customer it might be able to carry. So just another consideration. Beyond that, it also largely depends on what kind of flying you want to do. So if we're controlling an aerobatic plane, trying to do loops and barrel rolls, then maybe a more nonlinear or advanced controller would be, or model-based controller would be ideal. But then, of course, that also brings up the trade-off that if we want to go into these crazy kind of conditions, do we actually have a model that's high fidelity or reliable enough to use in these model-based control approaches? For example, for the aerobatics case. Otherwise, if we go for the level flight, nominal conditions, one altitude, probably just about any of these control approaches would work, even with somewhat mid-range fidelity model. But then often people will revert to the cascaded PID loop. This is a model-free approach, of course, so it's quite widely used. For this lecture, we will go with the cascaded PID loops control approach. So then now let's look at the plant. So our inputs to the plant, again, throttle, elevator, aileron, rudder. Notice here that we have normalized actuator inputs. So these would actually be something like degrees or radians deflection, but just for our purposes, we'll do them normalized. Then the convention for this normalization, so what is a positive deflection? We will define it here as a deflection that causes a positive moment. And there'll be some diagrams over here in 1 second that will describe this a bit better. But one more note on the ailerons themselves. So the ailerons need to deflect up and down on either wing to induce some kind of roll moment, but there's a thing called differential, which is often applied to the aileron deflection, which means we're actually using a bit more up for the same amount of down, for example. And this is a common thing used to combat adverse yaw, which is the tendency of the aircraft to yaw in the opposite direction that we're trying to roll. So that's just one more consideration, such that you know that the ailerons are probably not deflecting exactly equal, even opposite on either side, but with some differential as well. So now if we go back to our definitions of positive deflections, The elevator here, when we deflect upward, we generate a force downward on the horizontal tail, and then this gives us a positive pitching moment, so a positive elevator deflection. Now to the aileron, on the right aileron, we deflect up, that gives us lift down. Then we have the left aileron going down, giving us lift up. This then turns into a positive rolling moment, so positive aileron. Then last one here for the rudder, when we deflect the rudder to the right, we get a force to the left, which then yaws our aircraft to the right. So it's a positive rudder. So now to the states. These are actually the same 12 states we derived in the equations of motion. So body velocities, body rates, weather angles, and inertial position. So before we move on to which of these states we should feed back and or control, I think it's useful to think about where these estimates actually come from. So on board, we don't have direct measurements or perfect state information of all of these. So they must be estimated through a fusion of other measurements that we do have. So just to give a brief idea of where everything comes from here. So the most common measurements, for example, for the body velocities would be here the airspeed magnitude. So on TechPod, this is shown here with the pitot coming out the front and top of the plane. So trying to stick very far into the free stream so it's unobstructed by the fuselage or a wing. So even maybe about half the way down this probe, if the sensing were to happen there, there would still be some bending of the flow near that bulbous kind of fuselage. So the sensor itself, it's basically we get a dynamic a differential pressure from the pitot-static tube that we can combine with temperature and baro and then back out this airspeed value. So I put in parentheses here the slip and angle of attack because these are actually not so common to measure on small planes, but if one wanted to, airflow vanes would be one approach. So here on TechPod, we can also see airflow vanes. This is basically just a small little vane that can swivel about an axis point here and orient itself into the wind. There's a magnetometer, or sorry, a magnet and a Hall effect sensor on the axis. So then we can calibrate on the ground the position and then feedback our angle of attack, or in this left case, the slip. Probably more accurate than an airflow vane would be a multi-hole probe. And this is basically the same thing as the pitot-static tube, but there's more holes, more combinations, which at different angles, which we can then grab these airflow angles from. So lastly, part of the fusion process in most estimators for body velocities would be the GNSS velocities. So this is ground velocity. And these are normally quite reliable. So now on to body rates. We actually have somewhat of a direct measurement for the body rates from our IMU's gyroscope, but especially if we're considering MEMS-based sensors on small aircraft, then this gyroscope likely will have some bias and drift that we need to compensate in the, or estimate in the estimator. Moving on to the Euler angles. Even just from the body frame accelerations and their reading on the gravity vector, we can get a pretty good first guess of the roll and pitch angle. These, of course, have the same problem that the gyro did, that there's probably some bias and drift. But then once fusing these also with, for example, the GNSS velocities and the heading or yaw angle over here, the Euler angles can then become quite reliable. Further on the yaw angle, there is a just about direct measurement of this. It is a bit, it can be a bit off depending on where you fly. So basically the sensing principle here is an onboard magnetometer or compass. And this can be disturbed by quite a few things like power lines running through your plane or even just like metal in the ground near where you fly. So despite this, once used in some sort of estimator, it's generally a good constraining measurement for the rest of the states. So then finally, we have inertial position, which GNSS will give us directly. If we're not using RTK or DGPS, then we have to also be aware that the down position could be some 4 or 5 meters off, and the horizontal position maybe a couple meters off. So now that we know a bit where our state estimates come from and we know what our inputs are, we need to figure out how to control the plant. What should we feed back? How should we control it? So as I mentioned before, we'll use the cascade control PID loops. So here we see high-level controller, which we'll actually describe a little bit later in the slides. The main idea, though, is just that it's taking some paths or waypoints that we want to follow and acting as a position controller, which then gives some attitude and or airspeed reference to the low-level controller or the inner loop. So inner loop here for fixed-wing planes is often in aerospace terminology called just control, the low-level part, so low-level control. And if you hear an aerospace person tell you low-level control, they typically will mean stabilize the attitude, sometimes also with the airspeed in the same control. So then what does that look like if you're only stabilizing these, or stabilizing a fixed, let's say, low-level attitude reference, and you want to follow a loiter circle? Once we have any wind, we're going to start getting blown away by that constant drift. So this is where the high-level controller comes in, or in aerospace terms, the guidance level controller. So this is, again, here, the more kind of position tracking or maybe even a trajectory tracking controller that then gives us these attitude and or airspeed commands to the inner loop. So its job also then is to reject these low frequency disturbances, so like constant wind, and ideally end up here where we stick on the loiter circle even if there's wind. So looking a bit closer at the low-level controller, we can see there's kind of two different parts here. So in the front, we can call this like an attitude control section. So here we have the attitude references from the guidance, the feedback from the estimator, and then we also have a coordinated turn input here, kind of as a feed forward. And the coordinated turn equation we'll actually derive in a couple slides from now, so I'll get back to that one. But in the end, all you need to know for now is that this equation then gives us a reasonable yaw rate reference to give to our aircraft. So now that we have all of the Euler rate references, we can transform them into body rate references, feedback the body rates, go through a PI controller, and then also sum this with a feed forward control for the body angular rates. And this feed forward control actually should be noted that if one were to look at this not as two separate attitude and angular rate controllers, but as one global attitude controller, effectively this feed forward term acts something like the proportional gain for a PID on attitude control. And then the P here for the angular rate would be something like a derivative term, and then the I is a bit mixed in between all of them. So then after all this, we get our actuator outputs, elevator, aileron, rudder, and our throttle is just passed directly from the guidance to the plane. So a couple notes or warnings of caution. So if we have an integrator, we do need integrator wind-up protection. Basically anytime you're flying with a fixed wing, you should really always scale the actuator output with the airspeed squared. So this is kind of a dynamic pressure scaling, at least proportional to. And this is done because the each of our actuations, so our control surfaces are actually generating some kind of moment by bumping up the force on a given section of the wing. And we know from our lift and moment equations that the force and the moment is proportional to the velocity squared. So if we want a given error in our controller to correspond to a basically equivalent force or moment applied, then we need to scale these actuators by the airspeed squared. So then last note here, a quite common recommendation for controllers is just that the inner loop should somehow be a bit faster than the outer loop. So now let's get back to that coordinated turn. So this is also called steady level turning flight. So we can see we're flying on some loiter radius here, and at some airspeed, thrust and drag should be canceling each other out. And then in order to stay on this loiter radius, we of course need some kind of centripetal acceleration or force. So for turning flight, if it's steady, it means we are unaccelerated. So we see here, this is no body velocity accelerate, or let's say body velocity rates, and then here no body angular acceleration, so 0, 0. What this doesn't mean is that we cannot have body angular rates that are constant. So here we actually definitely would have a constant body angular rate, but the acceleration should be 0. So now level is referring to the flight path angle, so just 0. The flight path angle should be 0. With the slip also set to 0, this typically then implies that the pitch angle and angle of attack are equivalent. And then for turning, we almost always will need to be rolling. So one could imagine a large rudder on the plane used for directional control and sticking on some kind of loiter, but especially with vertical tails rising a bit above the CG of the plane, doing such an approach would likely still result in some kind of roll that wasn't planned. So in general, roll is the more efficient, easier way to conduct a turn. So then another thing for coordinated turns specifically, so the definition requires that we have no side force. So just to remind, the side force is an aerodynamic force, and so since we assume in this lecture that this must be 0, so no slip, if we slip, we will surely have some side force. Then the only force left actually is this centripetal force. And so now we need some other way to get this. Here we can grab this by actually banking the plane and taking a component from our lift and equating it here to the desired centripetal force. And then this, if we look at the equations, so starting just with the z-axis balance, we can see that lift is then proportional to 1 over the cosine of roll. So that means if I increase the bank, then the lift needs to also increase to satisfy a force balance. Further, if we have a constant angle of attack, for example, thinking about the maximum angle of attack that we should fly at. So let's say if we give some buffer zone before stall and we say here's alpha max and CL max that we're allowed to be at, if we're already there and now we say alpha is constant, the only other parameter left in this equation to modulate is the speed. And so then we get this other proportional relationship of the minimum speed that we must fly at increases with this square root value. So now down to another useful relationship. So heading rate can be found for a given roll angle with a force balance. So again, assuming slip is 0. So here's our force balance from the other page. And then if we just kind of solve through, like divide the equations, rearrange a bit, then we can get down to So the heading and the yaw being the same here because there's no slip, to this very simple coordinated turn equation. So the same one you saw on the other page. And so why are we using coordinated turn to begin with? This probably should have mentioned earlier. It's basically just it's the most efficient way to turn. So you're expending the least amount of energy to do so. So again, here note that we assume that the thrust is acting only in the same axis as drag. So in reality, the thrust force will be maybe pointed a bit elsewhere, some vertical component added to the lift maybe, and then we would need to compensate maybe with some angle of attack or pitch angle for this. But in general, for this kind of simplified analysis, it's normally quite still a useful coordinated turn equation here. So if we then move on from the low-level controller to the guidance level controllers. So here, this is a very, very common lateral directional path following guidance logic. So it's running on, for example, the PEEPS4 autopilot, and there's a reason. It's a quite simple law. It's very effective. And so I'm going to go through a very simple derivation for this now, but know that for your exam, you don't need to know this derivation. But it's good just to kind of understand generally how these path following algorithms work, or how the lateral directional guidance is done typically. Also in the exercise, we'll dabble a bit with these controllers. So starting out, we have some velocity and look ahead vector. So here's our velocity, we're flying with our plane. The look ahead vector is of some length L1, and then this vector gets connected to a point on the path. So then we have this angle between them, so the error angle eta. Using just these parameters, we can actually back out what the radius of this circle connecting the reference path to the aircraft's current condition, assuming we're something like a unicycle that can only fly in circles, which is mostly true for an aircraft. So we get this relationship then that we know what the radius is now, given the tuning parameter here, our L1 distance, and then our just feedback state, the error angle eta. So then from this, we can again look at this centripetal acceleration equation and plug everything in to get our control law. So this is where we get our lateral normal acceleration to the plane command. And this then can be interpreted in terms of a heading rate desired, which we can then plug back to this coordinated turn equation, which then leads us to our desired roll angle. So this is actually where we get that roll angle ref from the guidance module and then send it to the low-level controller. So there's the roll angle ref. So now the last high-level controller, this one's called the total energy control system. So it's quite old approach, but it's used often because it's again quite simple, and for at least constant altitude flying, it reasonably works. So here we're controlling the altitude and the airspeed. To do this, so what does total energy control mean? It means we are actually looking at energies here. So total energy is equal to the kinetic plus the potential energy. I'm sure you've seen these equations before. Then if we do a bit of dividing through, some more dividing through, and then a small angle approximation, we finally arrive here with our specific energy rate equal to this quantity. And so the specific energy rate is just basically this total energy, but divided by each of these steps, so by mg, mgv. So then if we move further, there's another term for text that's used in the controller, and that's the energy distribution rate. And so what does this mean? Basically, it's the rate of the potential minus kinetic energy. So then we arrive omitting here the derivation to this value. So again, yes, defined as the potential energy rate minus the kinetic energy rate. So if we look at it in the block diagram, here we can see kind of like an outer loop, an outer loop. So for the height and airspeed control, so we have desired value, the actual value, some PD controller, again, PD controller on the height. And then we get down here to the rest of the flight path angle and speed terms. So also here our specific energy rate error and our distributed energy rate error. In the end, the specific energy rate passed through this PI is mostly focused on our throttle setting, and the distribution rate is mostly focused on our pitch setting. Again, you don't need to know all of this on the text controller, but it's just good to get a bit of experience with it before the exercise next week. And there we'll be playing a bit around with the text controller and the L1 controller. So maybe some final notes on model abstraction. So in lower level loops, we'll model the dynamics from actuators to attitude/airspeed. So aside from computational costs, these dynamics are often actually pretty challenging to identify, at least in a high fidelity form. And this is one reason why linearizations are often made, because a linearized model, let's say from flight data, for example, is actually a bit easier to obtain than a full nonlinear one. Also, it's a bit easier to compute. So then if we go down to higher level loops, so often we'll use kinematics only approaches, and then something again like this unicycle vehicle, and doing some kind of position control. So this basically takes attitude airspeed to position. So then modeling on the model abstraction side. So I should note that both of these statements, so if you're thinking more on the control direction where you'd say, oh wait, but isn't the reference for attitude airspeed then getting transformed somehow into an actuator set point? Yeah, that's true, but here we're talking about what is our model describing? So here our model is describing the mapping from actuators to some resultant attitude and airspeed. And again here, some attitude and airspeed to some resultant position. So then in the modeling of these high-level dynamics, since it's model-free except for kinematics, I mean, we don't need identification, right? So there's no coefficients to identify. So that brings us actually to the end of the fixed wing controls and modeling lecture. Next week, the fixed wing case studies, you should definitely take a listen. So it'll be given by both Sebastian Fairling from Wingtra on the tailsitter hybrid platform, and then from David Rohr and Michael Onsbreck, who are PhD students in the Autonomous Systems Lab, and they'll talk about convertible or hybrid UAVs, actually a couple different examples of different formulations. It'll be a nice talk. So then also next week, fixed wing exercise. So we'll, as I said, play a bit with the control structures that were just introduced and in simulation, and kind of try to get a feel for how our developed aircraft model behaves with different control approaches. Okay, so hopefully this was informational for anyone who either has or has not heard of fixed wings or thought about them much before. And I guess happy listening, and see you in the case studies and exercise.